Torsion pendulum. This experiment is to determine the moment of inertia of a given disk by torsional oscillations and to calculate the rigidity modulus of the material of the suspension wire. Materials and apparatus required. Circular disk. Suspension wire. Suspension wire. Stop clock. Screw gauge. Identical cylindrical masses, 2 numbers. Torsion pendulum consists of a metal wire clamped to a rigid support at one end and carries a heavily circular disc at the other end. When the suspension wire of the disc is slightly twisted, the disc at the bottom of the wire executes torsional oscillations such that angular acceleration of the disc is directly proportional to its angular displacement and the oscillations are simple harmonic. Now, we will move on to the procedure of doing the experiment. Form the torsional pendulum as shown. Measure carefully the length L of the suspension wire between the two chucks. Length L of the wire between the two chucks. L is observed to be 75.6 centimeters. Now, make a mark on the side of the disc when it is at rest as a reference point. Standing in front of the pendulum, gently set it in torsional oscillations. So first we have to make sure that the angle of twist exerted on the disc is small. Then there are a few precautions to do before proceeding with the experiment. So first one is to make sure that the torsional pendulum is not having lateral movement during the rotational oscillations. That is, the pendulum should not wobble up and down. And then the next thing is that we should allow sufficient transient time between measuring the time period of oscillations. So this is for the oscillations to become steady. Then measure carefully the diameter of the wire at 5 different places. Find the diameter and then calculate the radius. So last point to remember is that the equal masses should be placed diametrically opposite with respect to the center of the disc. Now I will tell you how to note down or count the oscillation. So now this we have taken as the reference point. So this point will move from the center towards your left, then come to your right to the same distance and come back to the center. So this is one oscillation. So starting from the center to the left, then center, then right and to the center. This is one oscillation. So now we will start proceeding with the experiment. So the first step of the experiment is to determine the time period for 10 oscillations when no masses are placed on the pendulum. So now let us start counting the oscillations. I am going to switch on the timer at the same time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we see, the time period of oscillation is around 30 seconds. The next step is to place two masses or equal masses at a distance that is closer to the central chuck or that is near the central chuck. So now we are going to measure the distance between the center of the chuck and the center of one of the mass. So this distance is D1. D1 is noted to be 3 centimeters. Once we place the masses closer to each other like this, then we are going to make the pendulum oscillate again and then note the time period for 10 oscillations. Now we have placed the two masses closer to the central chuck and we have made the pendulum oscillate. Now once the oscillations get stabilized, we will start counting the number of oscillations and start the timer at the same time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the time taken is seen to be 34 seconds. So the final step of the experiment is to place the two masses further apart. So we have placed it at the corners of the disc such that the circumference of the mass coincides exactly with the circumference of the disc. So once we place the masses like this, we are going to measure the distance between the center of the chuck and the center of one mass. So this is D2. D2 is observed to be 4.5 centimeters. Once this is done, we are going to set the pendulum in oscillation. So we have set the pendulum in oscillation. We will now start counting the number of oscillations and note down the time period for 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the time period of oscillation is seen to be 36 seconds. Now the final step of the experiment is to determine the diameter of the wire at 5 different points and then to determine the radius of the suspension wire from the diameter. So in order to find the diameter of the wire, we are using a screw gauge. So we are going to place the screw gauge at 5 different points and then note down the readings. So we have put the screw gauge at one point of the suspension wire. Now the PSR reading is observed to be 1 mm and the HSC is seen to be 29 divisions. So like this, we are going to place the screw gauge at 5 different points and determine the diameter of the wire.
So this is the tabular column for determining the time period of oscillations. We have first measured the length of the suspension wire and it is observed to be 74.5 centimeters. Then we are going to make the pendulum to oscillate and take the time taken for 10 oscillations while we place no mass on the pendulum and while the masses are placed at closest distance and while the masses are placed at maximum distance. So first, when we have no mass placed on the pendulum, the time taken during trial 1 is seen to be 30 seconds. During trial 2, it is seen to be 31 seconds. The third column says mean. So we are going to average these two readings. So on averaging, the mean is seen to be 30.5. Then the last column says time period for one oscillation. So divide the mean value by 10. So we have 3.05 to be the time taken for one oscillation. In a similar manner, when the masses are placed at a closest distance, we are going to first measure the distance between the central suspension chuck and the center of one mass, and the distance is found to be 3 centimeters. Here again we are going to make the pendulum oscillate, and we have noted down the time taken for two trials, and then we have found the mean value of the trials and calculated T1. Likewise, when the masses are placed at the maximum distance, the distance from the central chuck to the center of one mass is measured, and it is found to be 4.5 centimeters. And two trials have been performed in order to see the time taken for 10 oscillations. Then the mean has been calculated, and then T2, the time period taken for one oscillation when the masses are placed at a maximum distance, is calculated. So the next table is to find the radius of the specimen, and this is done using a screw gauge. So the least count of the screw gauge is 0.01 mm. The zero error in the specific screw gauge taken is +3 divisions, and the zero correction is seen to be minus 0.03 mm. So we are going to take the readings at 5 different positions on the suspension wire. So at some first position chosen, the PSR is seen to be 1 mm and the HSC is seen to be 29 divisions. So at the second position, PSR is 1 mm and HSC is 25 divisions. At the third position, the PSR is again 1 mm and the HSC is 30 divisions. At the fourth position, PSR is 1 mm and HSC is 26 divisions. Finally, at the fifth different position, the PSR is observed to be 1 mm and HSC is observed to be 23 divisions. So now let me tell you how to calculate HSR. HSR is nothing but HSC into LC. So HSC value is 29 for the first case. So the HSR value is 0.29. Now observed reading is calculated by adding PSR and HSR. So we have 1 plus 0.29, which is 1.29, and finally the corrected reading is the observed reading minus or plus 0 correction. Here we have the 0 correction to be minus 0.03. So the corrected reading is 1.26. So in this similar way, we have calculated the corrected reading for all the 5 readings that are taken, and we have taken a mean for the 5 corrected readings, and this is the diameter of the wire. Now we have to determine the radius of the wire. This can be obtained by dividing the mean diameter of the wire by 2. So the mean diameter of the wire is equal to 0.62 into 10 to the power of minus 3 meters. So these are the formula for calculating the moment of inertia of the circular disc and rigidity modulus of the wire. So first we have to calculate the moment of inertia of the circular disc. We know the masses that we have placed. So we have placed 2 equal masses. So of that we can put the value for one mass. D2 and D1 have also been shown in the table, and T0, T1 and T2 have been obtained from the table. So on substituting all these parameters, we will be able to arrive at a value for the moment of inertia. Likewise, for the calculation of rigidity modulus, the formula is also given here. So once we have calculated the moment of inertia, we need to substitute it in the formula for the rigidity modulus, and apart from this, we need to substitute the value of the suspension wire, length of the suspension wire, and also the radius that we calculated from the table for the screw gauge in order to arrive at a value for the rigidity modulus of the wire. So the rigidity modulus and moment of inertia have been calculated, and the moment of inertia of the circular disc I is seen to be 1.59 into 10 to the power of minus 4 kilogram meter squared, and the rigidity modulus of the suspension wire is observed to be 4.369 into 10 to the power of 10 Newton per meter square.